My name is Ty Tuff. I'm one of the data scientists in Earth Lab, and part of my task is to work with one of our associates, which is NC Cask. And so I've been doing that over the last year, helping develop out this Climate Futures Toolbox, our package. So that's what I'm going to talk to you about today. If you go to Earth Lab's GitHub page, on there you'll find a repo for CFT. And the Climate Futures Toolbox is part of a larger suite of things that we're doing at Earth Lab and at NC Cask, which is all about making useful insights easier to gain. So on the left, you see that we have some generic online data repository. And on the right, we have a map that actually shows differences in precipitation between national park systems. So a lot of us have wanted to go and ask a question. We've gone to an online data repository and found the place fairly overwhelming. There may be new data formats. Maybe the data is too large to get down on your computer. Maybe the jargony documentation is just too much to handle. And so we really set out to just make it really easy to get data for people who just want to make decisions or find insights into what's going on around them. So we have a couple suites of packages that do these, and the one I'm talking about today is CFT. So what am I going to focus on in today's talk? Well, first, what is CFT and how do you get it? So how do you acquire it yourself? How do you, once you have CFT, how do we get and read data from this data repository? Then we're going to go look at how to search through that menu of available data and pick the data we actually want. Grab some available data from either a date or a place. And then we'll finally talk about maybe how to aggregate those into different features. So when you want to add up what's going to happen in your polygon, for example. So let's start with just what is CFT and what does it do? Right? CFT just helps you download data, and not any data, one specific data set. And this data set is called the MACA data set. And the MACA data set, this is sort of hard to read on this slide, and I apologize, but it says multivariate adaptive constructive analogs. This means statistics. So this is a statistical way of downscaling other climate models. So if you see on the left, there are 3 different maps, one at 500 kilometers by 500 kilometers, the next one at 100 kilometers by 100 kilometers, and the next one at 50 kilometers. That's downscaling. So we're taking coarse resolution and making finer resolution. There are several ways of doing this, and MACA is one way of doing that. I'm going to give you some details. Okay. So first, let's talk about what's being downscaled. Well, the thing that's being downscaled is called a global climate model. So what happens, we set out weather stations across the globe. Those weather stations collect weather information across space and vertically in the air. We also send out weather balloons, and we have satellites. Have lots of ways of measuring the conditions within those squares. Then massive supercomputers run computational fluid dynamics models to watch gases move around and heat up and pick up water and drop water and condense and decondense and move vertically and horizontally and mix. Now, those models are pretty expensive to run, expensive in every way you can think. They take a lot of time, but they take a lot of money to buy a huge computer and spend a lot of electricity to run that computer for a really long time. It takes a lot of experts to run these things. And so we wind up getting a scale that looks like this. The details here are not super important. I'm going to just talk about the trend where, so on the x-axis, I have how big of space do we think about? And on the y-axis, we have how big of time do we think about? So these global climate models are usually up at the top right-hand side of this graph, where we're thinking about large spatial extents over large expanses of time. And that's what the computer is able to handle. When we start thinking about, okay, what happened on one day in Boulder, that gets really hard because we need to start downscaling these large fluid dynamics models into something that's meaningful on the ground, like what was the temperature that we experienced, how much precipitation fell. And so one way of doing that is to run those fluid dynamics models at a smaller scale, but that's pretty expensive, and the results aren't that great. There's a valley in Gunnison, Colorado that's notorious for sort of giving bad results in downscaling because the valley is so deep and has such anomalous weather conditions, climate conditions inside of that valley, that it often isn't reflected just outside and for the rest of that square or that quadrant. So one way that you can go down is, just as I said, more complicated fluid dynamics models at a smaller scale. But because of the unreliability of that and because of the expense of that, people often do this statistically instead. So you take the big fluid dynamics models that are happening at large scales, and you try to use statistics to chop them up and project them down into smaller scales. So here on the left, you have a generic representation of this process. So we have these large climate model scale squares at the top. These are summarizing those fluid dynamics models. But then we can add new variables to connect that large scale to a small scale, right? This can be hydrology, this can be vegetation, topology, urban infrastructure, urban built environment infrastructure. And all this helps you give a more precise answer to where one particular place on the ground might look compared to the large fluid dynamic model that's happening above. On the right, you see different ways that people try to do this downscaling statistically. So the top one is a simple interpolation method where you just take those large scales and you interpolate them down. And this has a fairly high error rate because you're amplifying any of the internal errors of the climate model, you're amplifying under the surface without any type of correction. The second one down is a bias corrected version. So you sort of correct so that any biases that are coming in from the global climate model can be sort of washed out, and you get a regionally clean version of the climate model. The MACA, which is the third row and the sixth row, these are repeated. So 1, 2, 3 are the three models, and then 4, 5, 6 are those models again with slightly different conditions. But the third one, the MACA model, this one actually does what we see on the left, where we take multiple versions of data and we clump those together in a multivariate way to come up with a statistical estimate for what that downscaled climate cell should represent. So this has been shown in the literature to produce really good results, or sort of the best results we can for statistical modeling. So that's the reason that this group now, this group that produced the data that we're downloading today, that I'll loop back to them at the University of Idaho, they went through the effort of running all these computations for us, but they had to limit their spatial extent. So what you're seeing here is how much calculations they did, how much of the surface they calculated. But you'll notice some big black holes. Just because they cut off at a whole number latitude, the bottom of Florida gets cut off. So one of the very first issues we had with CFT was that someone wanted to look at the Everglades, and we can't really get all of the Everglades. And this is just because this is a huge effort and they had to sort of limit it someplace. You also notice up in the eastern side of Maine, some of that point got cut off, and on the west coast, you get some of upper Washington get cut off. So if you're really interested in sort of coastal dynamics, this data set isn't that great because it also excludes Hawaii and Alaska and some sort of important national parky areas on the coast. That said, it still includes a lot of really wonderful data. Okay. Now, these downscale data are not stored contiguously. They are stored in these columns of summaries. So you can see the purple one at the top shows a really tall summary of a particular point. So this statistical method will take a chunk of space in a cube, and it will summarize that down to a single point in its centroid, and you get this tall stack of data signifying all of the data that you calculated through time. Okay, so that could be max temp, mean temp, min temp, temperature, precipitation, humidity, whatever you want to do, and you stack all these in these thin stacks. On the right-hand side, you can see ways that you can immediately start using these stacks for analyses. So if you start coloring these stacks by temperature anomaly per year, as they have here, you start to see where it's been hot over a bunch of years and where it's been cooler over a bunch of years. And you can identify hot spots and cold spots really nicely. But this is without even downloading the data. Okay, these are the data themselves. They're just the structure of the data that we're going to try to retrieve. The big message here, though, is that these are too big. This is too much. This is 20 terabytes. If you can get it chopped up into small pieces and get it to your computer, it would take up 20 terabytes on your computer. But you have limits in how much you can ask for. We have limits on how big of packets we can move down the interwebs. And so we need clever ways to go and just get the data that we want, right? So this is like, if you are hungry and need to make dinner, you're not going to go get everything in the entire grocery store and bring it to your house. You're going to go and just pick out the few items that you need for your menu. And so that's sort of that's going to be one of the themes as we're going forward, is just how do we be really selective with the data that we want to choose, and how do we choose it in a way that's sort of meaningful for the questions we want to ask. So this comes down to how do we cut this cake. So on the left side, you're seeing what we're going to do today, which is take really thin slices of a lot of those pillars. So we can get something like temperature, maximum temperature on a particular day for an entire national park. What the part 2 was that we did on Tuesday was, how do you get an entire pillar, all of that huge stack of data, if you wanted to do something like run a long model over the entire time series, over all the data or something. As we move to looking at the data, and we're going to switch over to R, I want to emphasize that CFT is built on sort of 2 fundamental R technologies. One is that we have just adopted all of the tidyverse syntax. So there are sort of 2 worlds in R, the base R, which it was originally developed on, and then this new tidyverse piping syntax that has come about in the last couple of years, and we adopted the tidyverse syntax. The other thing that we've done is spatially, we've adopted SF and star spatial objects. These are different than many of the historical spatial objects that you guys have dealt with, like rasters or RGeos type of objects. So just as if you're trying to fit this to old code, or if you're having troubles trying to fit some spatial object that you have into this, you probably just need to convert it to an SF object, and then it'll probably work just fine.